quantum mechanics deals with de Broglie's hypothesis. De Broglie is a scientist who believed that nature loves symmetry. So whatever happens in nature is according to the laws of symmetry, and it obeys laws of symmetry. So he felt like if light obeys, like exhibits both particle and wave nature, why can't all the other objects exhibit both particle and wave nature? So he strongly believed that wave nature is exhibited by all the other particles. It can be shown by macro particles like football or any macro object, as well as tiny particles like electrons. So, particle nature of light. Light is considered to be discrete particles of quanta known as photons. These are treated as particles. Each photon has frequency nu and wavelength lambda. So, light also exhibits wave nature. De Broglie's hypothesis. According to de Broglie's hypothesis, any moving particle is associated with a wave. The wave associated with particles are known as de Broglie waves or matter waves. The wavelength lambda of matter waves associated with a particle moving with velocity v is inversely proportional to the magnitude of the momentum of the particle. Let us have a look at the equations involved in the de Broglie hypothesis. De Broglie wavelength of matter waves. E equals momentum into speed of light. So here we are considering objects to be moving with speed of light. So we are considering C over here. We can also consider V if any other object which is moving with velocity V is considered. So energy equals T into C. That is the first equation. And in the second equation we have E equals hc by lambda. This is for waves. So if we equate these two, Pc equals hc by lambda. Then we can cancel C on both the sides, and we have lambda equals h by p. The relation lambda equals h by p is known as de Broglie equation, and the wavelength lambda is called de Broglie wavelength. So we have three conclusions from this de Broglie equation. So when will the particle have lambda infinity? That is, when the wavelength of particle will tend to infinity. When a particle has zero velocity, then denominator becomes zero in the de Broglie's equation. So we can say that lambda of that particle is zero. So we cannot detect such wavelength. So it will be detectable only for moving objects. When velocity is non-zero, then only then we can detect lambda of such particles. If lambda is if velocity is zero, then we cannot detect lambda of such objects. And the other thing is, from the second point, we can see that whenever the mass of object is very high, then lambda will be very low. So we cannot detect such wavelengths because we don't have such advanced technology to detect very low wavelength. So lambda value should be in approximate range where we can detect the lambda. So the range of lambda is limited and restricted. So the particle should be very light. If the particle is light, then lambda will be comparatively high. So we can detect such wavelength with the help of technology, whatever we have. And third conclusion is, the smaller the velocity of microparticle, longer is the wavelength associated with it. This can be drawn from equation lambda equals h by p. P can be written as, that is p is momentum, right? So momentum is proportional to velocity. And we have these equations: half mv square equals q into v, where q is charge and v is potential. So we can find out the velocity, and then we can substitute in the equation lambda equals h by p. So we get this conclusion. And for particles in thermal equilibrium, half mv square equals 3 by 2 kT. So in this, if we substitute this in the previous equation, that is lambda equals h by p, then we get this relation. In the next video, we'll learn more about de Broglie hypothesis and Bohr's equation.